I guess we can get started. Today it's a great pleasure to have Professor Hongkun Park from Harvard visiting us and giving a talk at this very nice seminar series. And to be honest, I think among the two of us, I'm the one who needs more introduction. So he's a very famous professor. I'm new here. I joined MIT physics department in January this year. And my name is Long. Okay, so back to the theme. Hongkun obtained his bachelor's degree in chemistry from Seoul National University in Korea, and his PhD from Stanford. After that, okay. I'm sorry. And after that, he moved to Berkeley to work with Paul Alivasato and Paul McCune, two Pauls. And he got hired by Harvard in 1999 and was doing incredible work. So Harvard decided to offer him the full professorship in 4 years. Well, I wish I can get tenure in 4 years. And now he's a Mark Hyman Jr. Professor of Chemistry, as well as a professor in Physics Department at Harvard. So Hongkun has been truly a pioneer and a leader in the field of nanoscience. Through his career, he has made seminal contribution to, so-called molecular electronics by understanding the properties of nanoscale objects like fullerene, buckyball, carbon nanotubes. And then he also got interested in other aspects of nanoscience, one of which is to develop nano and microelectronic interfaces with living cells and neural networks. I'm sure he will be able to give an equally or even more interesting talk on that topic if you're interested. And another big direction of research is what I believe he's going to share with us today, is to explore solid-state photonic, optoelectronic, and plasmonic devices for quantum information sensing, so that he can realize solid-state all-optical information processing, which could enable ultra-fast computing with ultra-low power consumption. So there's a very, very long list of honors that Hongkun earned through years. I will just name a few of them. He got the Packard Fellowship of Science and Engineering at the beginning of the career, and the Ho-Em Prize for Science, the Miller Research Professorship from Berkeley, the NIH Director's Pioneer Award. He's also now a fellow of the American Association of the Advancement of Science, the so-called AAAS. Okay, so without further delaying, let's welcome Professor Hongkun Park once again to MIT, and please, it's your show now.
I'd like to thank Long for the wonderful introduction. I do not know who that guy is, but I'm the guy. I'm the poser from Harvard and across the Cambridge and stuff. So hopefully, I'll be able to not to embarrass my institution too much in front of really bright scientists and engineers here. So when Long invited me for this particular seminar, and I said, well, of course, I'd love to talk to and learn from the scientists and engineers at MIT, so I'd love to visit. And then he told me after that you'll be giving a talk at the Energy Initiative. And I said, I'm in trouble because I do not really work on energy research per se. Although the science and technology that we are working on may enable new types of technologies that may impact the, say, energy research in the future, what we are working on currently should be considered as fundamental science of materials. So if you actually are expecting me to talk about energy policy, I can tell you right now, nope, I'm not going to talk about that. I'm going to give a talk on science and engineering of low-dimensional materials and then how it might lead to new optoelectronic devices. But I promise you that I will try my very best to make it communicable with scientists and engineers here. And then I know that many of you are way more smarter. Actually, all of you are way smarter than I am. So I'm sure that you'll be able to understand everything that I say. So, let's go from there. And then hopefully I'll be able to entertain you a little bit, at least, by being silly. And I am quite good at that. So that one I'm quite good at. So let's start with an introduction about my research group. As Long said, my research group specializes in nanoscience. We make small nanoscale materials and develop tools for studying them. Then, once we have those nanoscale materials and tools, then we apply them to a wide range of problems, spanning physics, say chemistry and biology, and biomedical research. So on the one hand, we are working on so-called solid-state quantum optics, which we're going to talk about today. On the other hand, related to the first research, we are developing small nanoscale quantum sensors that can be used in chemical and biological research. And the third research area that we are also working on is this so-called nanobio interfaces. Basically, we are generating a computer chip that can be interfaced with brain slices and then actually live animals, and then use that in order to learn about the architectures of the brain. But for today, we'll concentrate on our solid-state quantum photonics effort. Now, how do I introduce this particular section of my research group? We can probably start with this, especially considering that we are talking about MIT Energy Initiative. Let's start with a brief introduction about information technology. What do I know about information technology? Not much. But I do know that they are built on two pillars. They are built on electrons and photons. We use electrons to process information, and we use photons to transmit information from one place to the other. And there is constant interconversion of information between these two physical media, electrons and photons. And we know that there are many good reasons why we rely upon those two distinct media. For example, we tried for a while to do everything using electrons, and it turns out that that is, in terms of efficiency of energy consumption as well as speed and power consumption and what have you, they were not exactly optimal. So we decided to put down the fiber optics, convert information that you actually computed using electrons to photons, and then transmit from over long distance. We actually have done that, and it works beautifully. It actually provides the foundation of information technology, right? But people actually have been wondering whether it is absolutely necessary. What happens if you can do everything using photons and photons alone? Then in principle, if you could do that, then you might be able to build faster, lower energy consumption circuits, and then do information processing. And if you can push it all the way down to individual photon level, then you might be able to even generate a quantum computers out of them. So a lot of scientists and engineers were interested in developing all photonic integrated circuits, and that's one of the research areas that we are working on. We are interested in science and technology that might enable these types of things. Now, you might say, well, that does not sound that bad. How bad can it be? Why don't you just make them? Because it looks nice looking circuit. Well, it turns out that this is not an easy thing to do because of the reasons that you are all familiar with. It turns out generating even the simplest possible switches, for example, out of photons and photons alone is a very difficult thing to do. And the reason why can be summarized using this particular slide. It turns out that lights do not interact with each other that well. For example, even the world's most powerful lasers, if you start to cross them, they never make a bang sound and you can actually just lightsaber kind of thing. Actually, they just pass it through. So you cannot block one photon using another photon, and then generating all photonic switches or transistors is a very difficult thing to do. So that's one of the reasons why it is very difficult to generate all photonic integrated circuit. Now, is it impossible? Well, it's not impossible. It turns out that atomic physicists actually have been doing things like that for a long while. So basically, what they are leveraging is so-called strong light-matter interactions. Basically, what they do is to make the light to interact with matter, like atom, strongly, and then make that atom to interact another colored light later, so that you can introduce strong interactions between light, between them. Using this phenomena and by leveraging them, you can actually generate lots of interesting looking phenomena. For example, you can block, say, propagation of photons using another photons and what have you. You can do all sorts of different things, and atomic physicists have been doing that for a long while. So what we are trying to do is to import the ideas from atomic and molecular and optical physics into the solid state realm, and then generate integrated devices where we can use the same principles to generate integrated quantum optical circuits. And not only we want to generate working devices, but we want to generate working devices that work all the way down to the individual photon level, so that we might be able to work with individual photons and generate a quantum circuits and stuff. And that's the goal of our research group. Now, this is a tall order, and then there are lots of different things that we need to do in order to make this realizable, but at least this is the type of dream that we have, and we are making an effort toward that goal. Now, in order to realize this, you actually have to work on lots of different things. And so indeed, my group actually works on lots of different experimental platforms to explore the possibilities of so-called quantum optoelectronics. One of the things that we are working on is so-called color centers in diamond. For example, nitrogen vacancy centers or silicon vacancy centers, which it turns out act as a really nice solid state atoms. Essentially, they can be considered as trapped atom in diamond. And then we can use them in order to generate quantum circuits, and we are working on that. This is actually a piece of diamond which contains so many of those trapped atoms. So when we actually shine the green laser, they start to become red. They can glow red. And then these are kind of things that we are working on. So if you actually happen to have a spare diamond, you can donate. Bring it over. So I'll be able to use it. The other thing that we are working on in terms of experimental platform is these 2D materials. And then we'll spend a lot of time explaining what I mean by these 2D materials, and then we're going to talk about what excitons in 2D materials can do. And of course, if you actually have these matter, at the end of the day, what we want to generate is a photonic circuit. So you actually need all those different types of nanophotonic elements and plasmonics elements so that you can couple those things together, so that eventually what we actually get is all photonic circuit. So all these types of efforts are going on in my research group. So today, we'll focus on excitons in 2D materials and what kind of things that we can do. So what do I want to talk about today? One particular material system that I want to focus on today is these transition metal dichalcogenides. These look like this, but you can essentially consider them as atomically thin semiconductors. So these are not metals. These are not, well, semiconductors are technically, physically speaking, insulators, but these are not wide bandgap insulators, but they are semiconductors. They are semiconductors that can hold optical excitation known as so-called excitons. Basically, when you shine the laser light into these atomically thin semiconductors, then it will move electrons from the valence band to the conduction band, generating electron-hole pairs. And they bind together to generate so-called excitons. Okay? So it's like generating hydrogen atoms inside these solids or sheet of materials. And these 2D materials come in a variety of different flavors. By changing the composition, you can change the band gap. So you can actually change the colors of those materials at will by changing the composition. And because of the fact that they are atomically thin sheet of materials, you can actually stack different materials together to generate so-called Vannevar structures. And we'll talk more about it later. So there are lots of different flexibilities that these two-dimensional atomically thin semiconductors give. And what we are trying to do is to use them as a canvas to define a variety of different types of optoelectronics elements. And that's the talk that I'm going to give today, the research efforts toward that direction. So today's talk will be organized in the following way. First, I will start to talk about generating as perfect a canvas as possible to draw the optoelectronic circuits. Once we introduce the idea, then we will demonstrate the perfectness of our canvas by demonstrating electrically tunable mirrors that is atomically thin. And then after that, we'll start to add a twist to the story and then see what kind of things that we can do with those twists. So first, about the canvas. And this is an obvious thing, although a lot of people just gloss over it. So let's say that you want to generate a complicated looking circuits on those two-dimensional canvas. Or, using this particular analogy, let's say that you want to draw a nice looking picture on a canvas. What do you have to do in order to get that happen? Well, you have to go out and buy the colors and then buy the brush and then you actually have to draw it and then stuff like that. But in order to do this, the first thing that you actually have to do is to buy a white canvas, nice white looking canvas. If you actually have a really dirty looking canvas, that you cannot, there are only so many things that you can do in terms of drawing pictures. The same is true for the semiconductor circuit. If you actually want to generate these nice looking computer chips, the first thing that you have to do is to put an effort to make as clean a wafer as possible. So that's what we are now trying to do in terms of when I say that we are trying to generate as perfect a canvas as possible. What we want to do is to generate optoelectronic circuits on top of that atomically thin sheet. And the first thing that we want to do is to make that atomically thin semiconductor as perfect as possible. And that's what we actually have put a lot of efforts into so far. How do you do that? And what do I mean by perfect semiconductor? Let me give you an example like this. So it turns out that if you actually get these materials in a variety of different fashions, you can actually grow them using so-called chemical vapor deposition method. And then some of the pioneers are here at MIT. Jin Kong's group are pioneering the efforts in that area. Or if you actually cleave them out of the single crystal materials using Scotch tape, that's what Andre Geim and other people actually got the Nobel Prize for in their graphene research and stuff like that. So if you actually somehow generate these atomically thin semiconductors and measure the optical properties, then it turns out that oftentimes what you get is these broad-looking, not sort of kind of featureless peaks. So if you actually get the best CVD grown samples and measure the spectrum, they look like this. And if you actually get the single crystal and then actually cleave them using Scotch tape and then measure the spectrum, they look like this. When I say that we want to make these material properties as clean as possible and make as clean a canvas as possible, what I mean by that is the following. I want to make these features as sharp as possible. And that gives you a measure of the quality of the materials. And the first thing that we did some time ago in 2017 was to show that when you actually start to passivate them using so-called hexagonal boron nitride, essentially wider band gap materials, then you can start to sharpen these spectral features much sharper. And then another thing that we actually have shown is that if you actually eliminate the substrate entirely by suspending these passivated two-dimensional materials, then you can actually make the materials properties even better. Why do I say that these properties even better than what we got previously in this particular spectrum? Well, though width-wise, it's not that much better. But it turns out that once you start to suspend them and eliminate the substrate, you start to eliminate some of the spectral features. Some peaks just go away. What does it tell you? Well, whatever this was, it is not coming intrinsically from the material itself, because the only thing that we changed it was to remove the substrate. Some spectral features stay the same, while some of the other features go away. So this must be coming from some interactions with the substrate. And most importantly, the following happens. It turns out that if you actually put these materials, atomically thin semiconductors, on top of the substrate, in this particular case, regular silicon dioxide, silicon wafer, then depending on where you measure the spectrum, spectral positions change quite a bit. And that comes about because of the fact that usually silicon wafers, however nice it is, silicon oxide actually holds charges, different amount of charges at different places. and that leads to this spectral position shift. But if you suspend them, then what you get is these lines. Wherever you measure in this suspended region, all the spectral lines overlap, which means that whatever you're measuring is intrinsic to the materials, and they are spectrally homogeneous, spatially homogeneous. And then, as I will show you later, that these lines are, in fact, as sharp as they can be. They are entirely lifetime broadened, if you like that jargon. OK, so you can actually do a bunch of different things, like passivating them using another wider bandgap materials and suspending them. You can actually make these spectrums as nice as possible and as sharp as possible. And then once you do that, you can actually use that fact in order to do lots of different type of things, like spectroscopy. These are the typical spectrum that people actually have gotten without actually all those optimization. But by optimizing the properties of those materials, you can start to get much sharper lines, which are much better defined, and as shown in here. And then this is especially for Bob field. You can actually start to do Rydberg spectroscopy of those materials, of excitons in these materials and stuff like that. So once you actually start to optimize the material properties, that opens the door to do lots of different things. And these are examples of that. But I do not want to spend too much time on these types of things, but rather I want to show you what you can do once you make as perfect a material as possible. And I will do that using an example of a mirror. So mirror is quite ubiquitous. Probably you have seen mirror or yourself in a mirror, say, or something like that. I tend not to like to do that because I know how ugly I am, so I did not watch myself in the mirror today. But the thing is that at least a lot of people watch themselves in the mirror. So mirrors are ubiquitous everywhere. One of the things about mirror that you often do not talk about or do not think about is the fact that mirrors should actually have finite thickness. Because depending on the mechanism that you use in order to realize mirror, whether it's a metallic mirror or dielectric mirror, you actually have to have something like a micron thickness in order to get the proper reflective surface. So all the mirrors that you see have to have, say something like micron or larger length scale thickness. In case of metallic mirrors, that thickness is limited by the skin depth of the metal. In case of dielectric mirrors, they are actually wavelengths of the light actually determines the thickness. But that does not mean that you cannot make a mirror thinner than these limits. At least for the resonant mirror, essentially a mirror for one particular color, you can make it arbitrarily thin. You can make it atomically thin. It works as follows. Let's say that you have a perfect semiconductors which can hold that electron hole pair known as excitons. And then let's say that you shine the laser light so that you can actually excite this exciton, which will then relax back to the ground state. During that optical cycles, it turns out that for the quantum mechanical reasons that this particular light that this exciton emits acquires pi phase shift. Basically, it destructively interferes with the transmitted laser light and constructively interferes with reflected wave light. So if you actually have a perfect semiconductors which can hold perfect exciton which is entirely lifetime broadened and nothing else, then this atomically thin sheet should act as a perfect mirror for that particular color. But of course, all those perfectness is not that easy to achieve. So even for the benchmark system like gallium arsenide quantum wells, which is another technical jargon, but the thing is that one of the systems that people have studied for a long time in order to perfect the material qualities, when they actually measure the reflectivities like this, they were usually about 3 to 4%. So what we decided to do was that, well, we actually spent a lot of time perfecting the properties of these atomically thin semiconductors. What happens if you actually shine the laser light? It turns out that if you just do that at cryogenic temperatures, like below 100 Kelvin, up to 85% of the lights gets reflected back immediately. They reflect back almost as well as gold metal. And then because of the fact that we can change their optical properties using so-called gating, meaning that by adding electrons or holes using the same mechanism that you use in order to make a transistor, field effect transistors. You can make the mirrors turn it on and off by just applying a few volts. And the reason why we can do that is because what we actually have put down is a perfect semiconductors, meaning that they are semiconductors that are holding so-called excitons that is entirely lifetime broadened. And then we can actually quantify that by analyzing the reflectance spectrum that we measure. In this particular case, the line shape looks like funnel line shape because of the fact that we actually have two mirrors in the system, one resonant mirror, which is embedded with one continuous mirror. And then Bob is sort of like, yeah, that is actually somewhat familiar with what I used to do, or what I still do. But anyway, so by analyzing this funnel-like line shape, we can actually independently determine the radiative rate versus non-radiative rate and then dephasing rate. And you can show that below 100 Kelvin, radiative process actually dominates all the other processes like non-radiative and dephasing processes, so that we can, and that's the reason why we get that high reflectivity. So this, you might say, well, generating a mirror at the end of the day, especially for one color, big deal. Yeah, it is definitely true. But the thing is that one important thing that this shows is that indeed these materials are as good as we can make them to be. And that's the important part. So, we published the paper and we were thinking about what to do with these kinds of things. And then one of the people who approached was these Starshop people. Do you know about this Starshop project? So basically what they are trying to do is to put the credit card sized mirrors in space and then use laser light pressure in order to propel them into the outer space. So that's actually a project that is going on at Harvard. And then, in order to do this, then they actually need a very, very light mirror, right? Low weight mirror. So one of the things that now we are trying to do is to put these TMDs, or atomically thin semiconductors, on top of these, and then trying to realize large-scale mirror-like things that works at cryogenic temperature. It turns out that in space, we do not actually have to have a liquid nitrogen and liquid helium in order to cool them down, so that's a good thing. So we'll see how this works out. But at least, some really, really sort of far out there kind of things, even then, you might be able to, say, at least play with them and then see where it can lead to. So that was one story about mirror. Let me briefly tell you about the other story about mirror, controlling the properties of the mirror using another mirror. So in the first example, we talked about the interference between reflected light and the light emitted by excitons. You can actually add another mirror so that we can actually generate another light that can interfere so that we can control the properties of these materials. So basically, it works as follows. So what we do is to use the same structure that we actually used to use, essentially suspended atomically thin semiconductors, and then add another mirror in the bottom. Then, by applying a voltage between the two, you can actually control the distance between those two, because you can essentially make a capacitor, make it go thinner, smaller and larger and stuff like that. You can control the distance between them. What happens if you change the distance between them when you shine the light, which is resonant with the excitonic transitions in this particular sheet? Well, it turns out that you can change the brightness of the reflection at will by the voltage that is applied that changes the distance between the two. And more importantly, you can change the line width quite a bit by a factor of 3 or 4. And by now, we can actually change it by a factor of 4 or something like that. So what is happening? Because it turns out that it can be easily understood using a phenomena that you might have learned in the Frenchman courses. So do you remember the wave reflection thing that you guys did as say, high school students? Probably high school, but I did not go through a very good high school, so I learned it in the freshman courses. So when you actually send the wave into the pole, and the pole is actually fixed, then when they get reflected, it actually generates those standing wave-like patterns, right? So depending on where you sit, sometimes in this particular location, for example, you will never see, you will see a maximum amplitude waving, and then in this particular location, no amplitude whatsoever. So basically, that explains the phenomena that we are seeing. So when you actually shine the laser light into the gold mirror, what you're generating is these standing wave-like patterns of electric field. And then what we are doing is to move those atomically thin semiconductors through that standing wave-like patterns. Sometimes those excitons see the maximum electric field, and as a consequence, they will reflect a lot. They will emit a lot of light, and then the line width will be large. And then sometimes they see zero electric field, so they cannot do whatever, so they actually emit very much small amount, and then the line width is very small. So these are, and then you can actually analyze all that using some equations, and then show that you can indeed change so-called natural radiative lifetime by a factor of 10 using this simple, essentially electromechanical systems. So again, this in itself might not become a real device as of yet, but the thing is that what this shows is that by engineering the environment of these semiconductors, atomically thin semiconductors, you can control their optical properties in a very controllable, precise fashion. So those are the kind of things that we are now trying to do. And of course, once you actually generate these suspended structures and change the distance, essentially this is a drum, so you can actually use a drum resonance frequency to change them really fast and stuff like that. You can generate light drums out of this. And then indeed what we are doing is to use those light drums to generate something that looks like a micromirror arrays using atomically thin semiconductors. So these are essentially drums that we generate. They are made of atomically thin membranes on top of those holes, and then we are changing the distance between them. I'm sure that it will not be as useful as mirror arrays, but at least we might be able to do some interesting things using them, like beam steering and other types of things. So that was the story about the mirror. Now, let me move on to talk about the twistronics, or adding textures to the canvas. So this one actually is probably quite well-known thing at MIT. Indeed, one of the most exciting developments in physics over the past 10 years actually happened in here. For example, when Pablo's group actually generated, say, superconductors out of twisted bilayer graphenes and stuff like that. And it's directly borrowing from that, but we are going to do that with the atomically thin semiconductors. But let me briefly introduce you about the idea. So I already showed you this particular view graph, so-called generating so-called Van der Waals heterostructures by stacking different materials together. And the reason why we can do that is because we are working with atomically thin materials which are weakly interacting with each other between the layers. Now, when you just see this particular picture, you might think that it might not be that different from what we already have in our technology. For example, when we are seeing the cascade lasers or other types of super lattices in everyday life, well, not everyday life, but the thing is in our technological things, then what we are using is these well-defined layers of materials which are atomically precise. So this might be just like this, maybe. But it turns out that in these two-dimensional materials, that there is additional degrees of freedom, which is related to twist, which is quite unique. Basically, because of the fact that this layer and this layer do not interact that strongly, you can stack them without worrying about atomic registry between the layers, at least in theory. Of course, in practice, it's not like that, and we'll get to that in a little bit. But at least you might be able to introduce in a twist so that you do not have to worry about atomic registry. And if you start to do that, then you generate interesting patterns when you stack them together. And they are known as moire patterns, and you might be able to use those moire patterns to do interesting things. And then, indeed, that's what Pablo's group did in terms of generating superconductivity, demonstrating superconductivity in twisted graphene, which was really exciting development. And there are lots of other people who are also trying to do that in these atomically thin semiconductors as well. In particular, atomically thin semiconductors which are different from each other by stacking them together. Now, these are exciting developments, but at the same time, these are the developments at their infancies, meaning that there are lots of different things that people are observing, but there are also a lot of things that people do not understand. So one of the things that we actually tried to do was to do a systematic study so that we can understand their properties better. And we wanted to do it in the simplest possible systems. So what we decided to do was to do optoelectronic characterizations of twisted bilayers made of the same materials, like tungsten diselenide, molybdenum diselenide, so that we can introduce as small a variable as possible. So the type of structure that we make is the following. So we actually generate twisted bilayers. Basically, we put one layer down, twist a little bit, and another layer down, but they are made of the same materials. And then we add boron nitride on both sides so that we can protect them. And then add another graphene layer so that we can use them as so-called gate electrode, or so that we can apply the electric field or change the electron density or hole density in this particular semiconductors. And this is actually this picture of the devices that we generate using so-called 180-degree sample and 0-degree samples. The most important thing is the following. It turns out that the twist degree of freedom, the twist angle that you introduce, have a profound effect on the properties of the materials. Without going into detail, for example, this shows one example of that. This is the same device. One region was 2 stacks, which makes 0-degree angle. The other region is 2 stacks making 180-degree angle. And then you can actually measure one particular optical properties, and you can see they are entirely different. And then we'll get to that in a little bit. But twist angle makes a humongous impact on the optical properties of these materials. The first thing that we did was to characterize a spectrum of these twisted tungsten diselenide bilayers. So starting from monolayers and then adding another layers, and it turns out that 180-degree angle is what happens when you actually have so-called naturally stacked bilayers. So this is naturally stacked bilayers. We flipped one of the layers over and then make a 0-degree angle, 2-degree angle, 17-degree angle, and measure the spectrum. One thing that you notice is that there are 2 groups of peaks, noted as X0 and Xi. What are they coming from? Well, they come from 2 different kinds of excitons. One exciton is coming from so-called intra-layer excitons, where electrons and holes are residing in the same layer. The other one is coming from so-called interlayer exciton, where electrons and holes are separated into separate layers. How do you assign which one to which? You can actually do so by measuring so-called Stark spectrum, by applying electric field and see how those lines shift. So what we are doing is to, in this particular geometry, apply the voltage between the 2 graphene layers so that we can actually apply electric field perpendicular to the plane of those atomically thin semiconductors. And then what we are measuring is the position of the peaks. These peaks do not shift as a function of the electric field. These peaks do shift as a function of the electric field. What does it tell you? This tells you that these peaks, at least species that are responsible for these peaks, do not have electric dipole moment perpendicular to the electric field. These ones do. That's what it shows. From this picture, you can tell this one should not shift as a function of vertical electric field. This one should. So we can actually assign this one to the intra-layer exciton, this one to the inter-layer exciton. That's nice. But one interesting thing is the following. So, if you actually measure the so-called degree of circular polarization of these peaks, they actually exhibit interesting variation as a function of the twist angle. So basically, in here, what we are measuring is the following. We shine right circularly polarized light into the sample and measure whether right circularly polarized light comes out or left circularly polarized light comes out. If the right circularly polarized light, the same circular polarization comes out, then the degree of circular polarization is high. And you can see that when in the natural bilayers, there is no degree of polarization for the interlayer excitons, while for the twisted angle, that there are high degree of circular polarization. Why? It can be understood rather simply. It turns out that in case of so-called natural bilayers, because there is no twist angle, that this is actually related to so-called spin valley degrees of freedom. The actual lattice looks like a hexagon, and as a consequence, the brilliant zone also looks like a hexagon. And then when you actually have a natural bilayers where one layer is sitting directly on top of each other, then one layer brilliant zone is sitting directly on top of the other layers brilliant zone, which means that there is no momentum or energy mismatch between the two different valleys. Sounds like a lot of jargon, and it is. I'm sorry. But the thing is that basically, there is no energetic cost of momentum cost of moving excitons from one valley to the other. And as a consequence, that process can be really fast, which leads to lower degree of circular polarization. But when you actually start to twist, then they do not match each other at the same location in momentum space, which leads to the slowdown of the process, which leads to higher degrees of freedom, a high degree of circular polarization. So if you did not like all those band structure jargon, that means that I failed miserably, and then I do not understand what I'm talking about, because I'm supposed to tell you what in a way that you are supposed to understand. But basically, what we are trying to do is the following. Essentially, when you actually have completely well-stacked monolayers, excitons can move from one layer to the other, rather in a facile fashion. So, and then that process leads to depolarization of circular polarization. While when you twist them, then they are now starting to separate in the momentum space, and as a consequence, they do not, actually mix that well. And as a consequence, you do see a large degree of circular polarization. You get that? Kind of. But more important thing is the following. When you twist them, you can start to introduce energy and momentum mismatch between two layers, which leads to different properties of those materials. And that can manifest itself as difference in degree of circular polarization. The same is true. Actually, that twisting actually leads to different behaviors when you start to dope them using, for example, holes or electrons, and then how they behave in terms of degree of circular polarization. It turns out that that valley mixings, which leads to low degree of circular polarization, can be completely turned off by doping them with essentially holes or electrons. And without going into details, that is also related with the fact that in the doping in these materials, that once you start to introduce twisting, then they behave quite differently in terms of adding electrons, holes to the system, which can lead to completely different behaviors. So without going, even if you do not understand exactly what I'm talking about, I do not understand what I'm talking about either. That's the reason why I'm failing. But the thing is that most important thing is the following. By introducing a twist angle, you can actually change the band structures of those semiconductors, which has observable consequences as a function of electric field as well as doping. And we can use those things in order to realize some interesting looking devices that can actually have an optical function. Okay? Those are the kind of things that we are now trying to exploit. So that was one easy example of what twisting can do. But another thing that we wanted to do is to see whether we can investigate in a much more detailed fashion. So let's end this particular talk by talking about this spontaneous texturing. So I already showed you this slide and then showed you that the twisting can lead to interesting pattern known as Moiré pattern. One thing that I did not tell you is that these are fiction, meaning that when you actually introduce these little angles, then atoms actually do not sit like this, but rather they decide to find more comfortable position and then reconstruct themselves so that we can start to generate these different domains. Because, for example, in here, these atoms are not sitting on top of each other, and then atoms do not like that. So they actually start to find a position that is more comfortable, and that leads to the formation of these different domains. And then one important thing is that those also has an important consequences. So if you look at different domains, then one thing that in the real space, for example, in terms of lattice structures, they look like this. And it turns out that one of the domains is known as AB, and the other domain is known as BA. Can you guess why we call them that way? Yeah, they are flipped versions of each other. This is a flipped version of that, and that is flipped version of this. Now, in different regions, we can start to tell top and the bottom. There is a preferred direction in these bilayers once you start to introduce these restructuring. There is a spontaneous symmetry breaking, and there is domain formation when you actually start to make them relax. And that has a direct consequence in the spectrum. So we can actually start to image them. And then this, I will not get into details, but the thing is that you can do that using both transmission electron microscopy or scanning electron microscopy. Basically, using electron microscopy in a dark mode, in this particular case, in a particular diffraction spot, or a twisted angle, SEM, you can actually start to image all those restructuring in nanoscale in those twisted bilayer samples, and then start to see whether they lead to observable optical consequences. And this one is actually something that I probably should not get into this one. Whenever somebody shows you these nice-looking pictures, be suspicious, very suspicious, because actual picture looks like this, and we are picking out this region and then showing it to you. So one of the things that we actually should learn how to do and how to improve at the moment is that although by twisting those two bilayers, we can generate lots of interesting patterns, as of now, we do not know how to control the disorders that well. So actual large-scale samples look like this, out of which we are concentrating on particular regions. So one of the things that we actually are now trying to do is to make those texts as perfect as possible so that we can generate these patterns in wide regions, in the wafer scale, so that we can actually start to use them to do some interesting things. So again, we can start to tell top and bottom, which means that when we generate interlayer excitons, then there should be difference between interlayer excitons where electron is sitting on top or electron sitting on bottom, right? There should be a preferred dipole moment. And we can tell that by making these samples, which is particularly disordered so that those domains are rather large, and then start to shine the laser light in different spots and measuring how they shift as a function of electric field. And you can see that depending on the region, one particular spot shifts in one particular direction, while the other spot shifts the other direction, which means that these are actually telling you exactly whether dipole moment is aligned with the electric field or anti-aligned with the electric field. And when we actually twist the bilayers and then generate a bunch of different domains, then you can start to generate different regions with a different dipole moment orientation. And there is a reason why it's actually happening, and the reason why we are seeing lots of other types of features. But most important thing is the following. By using this particular phenomena, we can now start to generate the exciton arrays where in one particular region, exciton is pointing one way in terms of dipole moment, and the other region, there is exciton pointing downward. So you can actually start to generate exciton arrays, tightly bound excitons that can be arrayed in a nanoscale fashion, and we are now trying to use that particular fact in order to make interesting devices. So these, without going into detail, these are the kind of things that we are now trying to do by making those arrays as nice as possible and start to trap electrons and excitons and holes into particular spatial patterns. It turns out, according to the theoretical calculations, that you can actually use those resources to make quantum simulators, because you can actually generate an exciton arrays, and those excitons are interacting with each other with a dipole moment. And then, as say Bladan here at MIT and Misha Lukin, my colleague at Harvard, actually have shown, you can use those resources to generate so-called quantum simulators, a primitive version of quantum computers. We can actually use those resources to generate so-called topological excitonics and metasurfaces as well. So one of the things that we are now trying to do is to learn how to control the degree of freedom as cleanly as possible and to make them as perfect as possible so that we can start to use those resources to define optoelectronic functionalities. So without further ado, let me stop there. So those were the stories about our efforts to generate atomically thin canvas for optoelectronic circuits. So one of the things that we decided to do was to actually realize optoelectronic functionalities out of those atomically thin materials. The first thing that we had to do was to learn how to make them as perfect as possible and start to manipulate them using a variety of different types of physical variables. And then most recently, we are now trying to introduce textures to those canvas so that we can use those as a resources to make interesting functionalities out of them. So let's end with the most important slide. As you can tell, all I do is just go around and give this kind of lousy talk and do not know how to explain things. And these are the people who deserve all the credit. So Yu Zhou is a person who actually started that two-dimensional materials efforts in my research group. And Jiho Sung is a person who actually generated those dipole arrays, essentially twisted bilayers and then exciton arrays. And Giovanni Scuri and then Trond are the people who actually measure the work on the circular polarization and stuff. And Ryan is working on a different project involving the 2D materials. And Hosuk is a person who actually generated all the crystals that we use in order to make those atomically thin materials. And then I also should thank our collaborators, Philip Kim and Michelle Lukin, without whom I would not have been able to do any of these things. Especially the whole reason why I got into these 2D materials was when Philip, who happens to be my college classmate in Seoul National University, moved from Columbia to Harvard. He said, we've been known each other for 30-some years, and we never worked together. Why don't we work together? And I know how to do transport spectroscopy. Why don't you do some optical spectroscopy? Why don't we work together? And that's how this whole project started about 4 years ago. So I indebted to him in terms of starting this entire project. And then I also should thank funding sources to make this possible. And thank you very much for your attention. Yes?
The twist is a little bit like chirality.
Yes,
And
indeed.
there's also some very interesting new spectroscopic techniques for measuring, looking at chirality
Yeah.
with three-wave mixing.
Yeah.
And I wonder if you could use the microwave spectroscopy to make measurements of the degree of chirality as a function.
Yes, absolutely. I think that is a very interesting suggestion, and then I think that should be possible. And then that was actually one really great way of actually introducing this particular subject. I actually bungled quite a bit about this particular DOCP, or degree of circular polarization, but basically what Bob said was exactly right. What we are measuring is to essentially, by twisting it, we are generating domains with the different types of chirality, and then we are measuring them using circularly polarized light, and the degree of circular polarization gives you a way of handling those different things. Yes, great way. So I will definitely use that, and then shamelessly steal that next time I explain things. Yeah.
Most of your slides used wavelengths of around 700 nanometers.
Yes.
So I'm wondering, how low can you go? Can you go into the X-ray part of the spectrum?
Oh, X-ray part of the spectrum in our experiment, you mean?
Well, using your principles.
Oh, well, you can go to the X-ray, and then that's what crystallography is about, and then that's how people determine the structure of the materials using X-rays. So essentially, they are using the interference of X-rays. It's scattered by the atoms in order to determine the structure.
The question is, can you build an optoelectronic device
Yeah.
that works on X-rays?
Yes. I think that the similar principles are certainly applying in the X-ray optics as well. For example, they use crystals at particular angles to deflect X-rays, and the principle, if you think about it, is very similar from what we actually talked about when we talk about mirrors and stuff. Yes, but the thing is that in principle, if we actually learn how to manipulate the matters, not in a nanoscale, but angstrom scales, yes, we should be able to generate the similar type of structures for X-rays, in principle.
Great talk. I'm I'm just curious if there's a value in twisting the twisted angle. Like if you want to do another layer
Yeah.
on top of it, and obviously that's going to change the light's polarization.
Yeah.
Different has this experiment been done? Like
No, not in these.
and if so, what is the point of doing it?
No, so that's a great question, and then that certainly introduces another variables that can be exploited in order to realize new materials properties. For example, in the atomically thin semiconductors, which is younger than graphene, that has not been done, but at least in graphene area, that has been done. For example, they generated triple layers of graphene and introduced twist angles, and it turned out that they not only generate superconductivity, but they also generate magnetism and other things. So it turns out that that can be used to introduce interesting material property. Yes?
Thank you for your wonderful talk. So how about integrate optoelectronics with topological materials
Yes.
of spintronics and
Yes.
even with superconducting materials,
Yeah.
like a thin film of IBCO or something?
Yes, and I think that that is a great experimental direction, that great research directions, and then a lot of people are interested in that. And then it turns out that one of your product, MIT product, Su Yang, actually is coming to Harvard as a faculty member in our department. And then once he comes into Harvard, I'm looking forward to learning from him, and then working with him in order to realize all those different things. Yes. So he's right there. He knows a lot more about topological materials than I do. I will ever do so. Yeah.
In the section when you were talking about using the TMD and the gold mirror below
Yeah.
it, and saying that that separation difference impacted the reflectivity of
Yeah.
the TMD,
Yeah.
how did you separate that out from the change in the TMD's electronic properties because of the strain that's induced by, I guess, dipping it down?
Yes, great question, and then thanks for pointing it out. And then it turns out that you can, we actually had to do a lot of control experiments to separate it out. But the thing is that this shift in the line positions, they are related with the strain that you are inducing into the layer by changing the distance. Essentially, by pulling the tent, you are generating a strain, and then that shifts the position. But it turns out that that does not change this line width. We can independently do that without the mirror, and then you can actually prove that. Yes, that is a great question.
Without the mirror.
Yeah. So basically, all you have to do is to shine the laser light where there's no mirror, and then see the position. Yes, that's a great question.
Hi, great talk, thank you. I just have a question. As you mentioned, for
Hi.
all optical computing, you would want to have some nonlinearities
Yeah.
and like photon-photon interactions.
Yeah.
How do you? Have you thought about how that would work in these materials? Because you mentioned it at the beginning, but there wasn't much detail.
Yeah. So that was. Thanks for pointing that out. And then indeed, we actually are working toward the directions. We actually can induce the optical nonlinearity by introducing a large number of excitons. That is small number, essentially small nonlinearity, but we actually have studied it in our paper. And also, we are now incorporating other nonlinear materials to amplify those effects to, do all those nonlinear optics as well. So those are the kind of things that we are actually actively working on. Exciton interaction generates nonlinearity. They are rather soft at the moment. Actually, we believe that before it becomes useful, we'll generate Bose-Einstein condensates of excitons first. So that actually is a complication. That's another research direction that I did not talk about. But the thing is that we are also coupling these atomically thin materials with nonlinear materials so that we can actually introduce optical nonlinearity into the system. Yes, great question. I should come here more often so that I can learn how to explain things and think about the new research directions. Yeah.
Hi, great talk. I guess I'm just wondering, so there's both rotation moires and lattice spacing moires.
Yes.
So does any of the stuff you describe also pertain to materials with different lattice spacing, or does it necessarily need to be the twist?
So in our particular case, the reason why we concentrate on homo bilayers was because we do not have to worry about lattice spacing based upon moires. But in case of heterobilayers, then you also have that as well. And then people actually are trying to exploit that as well. Although exactly how they will be decoupled from the rotational moire, remains to be seen.
Hi, I was wondering if you could comment on exciton diffusion across the domains in the
Yes,
twisted
that's a
bilayer.
great question. So disclaimer, essentially the letter second half is actually all the things that we are actively writing up at the moment, and that might be one of the reasons why it was rather, how can I say, rough. But another thing that now that you mentioned it, I will just quickly show you the data that I did not show. So if you are interested in exciton diffusion, yes, there is an exciton diffusion, and then we can actually use those exciton diffusions in order to, we can actually see the spectral signatures of exciton diffusion, which I did not tell you anything about. And then you can actually see you can actually investigate that quite readily using excitons. This is my student's talk that he gave 2 days ago, so it is rather rough. So I did not have time to incorporate it into my slides. But basically, we can actually change the Moore spacings, and then we can see how the spectrum changes. And then these spectrum changes actually are best explained by the exciton diffusions in these monolayers, both in between the layers and within the layers. So we believe that what we are seeing is exciton diffusion in these systems, and then we can actually study them as a function of the Moore pattern size, and then how it changes and what have you. So all those things can be studied, yes. And then if you are interested, I can show you more data about that. But didn't want to make a 2-hour talk, so decided not to talk about these.
Hi, thank you for a very good talk. I have a question that, as you have mentioned, in twisted bilayer samples, there's a problem of disorder and non-uniformity. And also, even if you have a very uniform sample, the domains of AB and BA can be smaller than a sample.
Yeah.
So I'm wondering, how can this twisted thing be useful in application?
So depending on the wavelengths that you're talking about, in terms of optical applications, metasurfaces and stuff like that, it'll not be as useful. But if you could make those Moore patterns as perfect as possible, I think that they can be used as a resources for example, exciton arrays and then quantum information processing. So that's one of the reasons why, when I talked about the metasurfaces, we talked about those pole arrays, which can be made into optical wavelengths, and then we can actually use the coupling between the different metasurfaces. So for metasurface applications, it'll be more useful, the classical thing. Moore patterns will be more useful if you want to generate closely spaced, nanometer spaced excitons that are interacting with each other. Okay? But making them as perfect as possible is a big challenge that we have to learn how to do. Hopefully, we'll be able to do that.
I had a question about the twisted bilayer stuff. Yeah. So there are bulk materials that, instead of 2D, just bulk materials that have hexagonal symmetries. If you grow 2 bulk materials on top of each other with a twist angle, do you also see kind of similar phenomena, or?
If you know how to do that, I think that you should be able to. But the thing is that, again, that was a point of this particular slide. When you actually grow them, bulk crystal into a bulk crystal form, it is very hard to change the atomic registry between the layers, because so they actually relax into the most comfortable thing. So that's the reason why you get the crystals, which actually have 180-degree twist angle all the time, right? So atoms, if they let them find the most comfortable position, they almost always find the comfortable position instead of actually make an interesting twist angle. So that is one great thing about this assembly strategy that opens up interesting avenues for physics and also material science and other things, that now you can actually grow them and then stack them with artificial angles so that you can actually do lots of different things. But as of now, I do not know the strategy. I'm not saying it's impossible, but I do not know a strategy to grow the bulk materials with controlled twist angle. I don't know anybody who knows how to do that. I certainly don't. The fact that I do not know does not mean that nobody knows, but the thing is that at least I do not know. There are lots of things I do not know. Yes?
You were mentioning the dipole, that sometimes you have excitons in a single layer as opposed to intralayer
Yeah.
conformation.
Yeah.
Could you, in theory, select selectively couple and form exciton-photon strong light matter interactions or form bilayers in specific regions of your material that only couple to a dipole with a certain orientation?
Yes. And then that's the final thing that I did not talk about, and there are some things that we are actually doing at the moment about using interlayer exciton and intralayer excitons differently. And then also, you can, this is another thing that I did not talk about, was that you can actually introduce the coupling between intralayer and interlayer excitons as well. And then we do the spectral signatures of that, and then you can actually use it in order to do some interesting things. You can actually, so it turns out that there is anti-crossing and other things that you can use, and then you can see, and then you can actually use it in order to move the information from one layer and then protect it, and then go back to the another layer. Actually, that's another thing that we are actually working on. But yes.
Bilayer graphene, we know that there is a magic angle where the interaction is strongest.
Yeah.
So for this TMD, do you think there is at least a range of angles that the interaction between layers gives you the most strongest signal or coupling between layers and can modify its property?
That's a very interesting question. There are multiple answers that I can give, but the thing is that the probably most basic and honest answer is that nobody knows. But the thing is that there are some theoretical calculations which suggest that in TMDs, the magic angle is not as stringent as in graphene. And also, in the problems that I talked about in terms of exciton interactions and exciton arrays, the magic angle is not as important as in correlated graphene systems. But the thing is that does not mean that it is not important, and then it just simply means that we have not thought about it carefully. There may be something interesting, may not be something interesting. We do not know the answer to that.
I have a quick question about the dipole excitons again. So dipole moments of excitons and emission direction is normally perpendicular to each other.
Yeah.
So for the interlayer excitons, I would expect the emission along the 2D materials. So were you able to, how did you detect it, or can you just distinguish the interlayer versus intralayer based on the emission directions?
Very observant question, although there is one thing that you actually have neglected. There are two kinds of dipole moment. One is a permanent electric dipole moment, and the other is transition electric dipole moment. And then all the Stark effect that we talked about was about the permanent electric dipole moment perpendicular to the plane of the materials, right? But that does not mean that the transition dipole moment, which are associated with the electron-hole pair recombining, is perpendicular to the field. But the thing is that they are, so some of the excitons do exhibit transition dipole moment perpendicular to the electric field, and then that's another thing that I did not talk about. They are so-called dark excitons, and then we studied them using surface plasma polariton. That's an entirely different subject, which I did not talk at all about. Yes.
How does the presence of defect sites in your material affect which will have a different energy scale than the moire patterns, for example? How does that affect your experiments with these other effects?
So one thing that we tried our very best was to eliminate the defect by generating a crystal which is clean as possible, and then learn how to passivate them and protect them. So for example, when we, at least in our sample, I can operationally say the following. We looked very, very hard for the so-called single photon sources which are attributed to the defects. In our samples, we have a hard time finding any of them. And that was one of the reasons why we could do a lot of different things. For example, if it were defect-ridden, we would never be able to make mirrors. We would never be able to see all those different things because the excitons tend to go into that low-energy defect sites, and then you actually see all those emissions. We do not see those defect emissions. That does not mean that they are not there, but at least spectrally, so far in our studies, it did not seem to affect our properties as much as some of the other studies. Yes. I'll be here to answer the questions, so we should stop. But the thing is that if you actually have any other questions, I'll be happy to learn and then answer any of the questions as best as I can.